Okay, today we're going to make a jump in terms of the topic that we're studying. So this will be our last unit per se, where we're going to work on gas laws. So with the type of learning that we've been doing, we've kind of made some jumps and we're not able to cover all the same material that you would have seen had you been in a normal situation. So I feel like the best concept to work on next is to work on gas laws. Originally with after the mole would follow what's called stoichiometry, and then we apply that to other topics, and unfortunately we just aren't going to be able to do that. So looking at what our units were and what we have left for time, I feel like this was the best kind of unit to move on to, so it's not a very smooth transition, but it's going to give you again some exposure, so that way if you find yourself in a chemistry class, we are going to be working with algebraic expressions, so then if you're taking physics next year, we're still getting a math component to get you ready for what your future science classes may be. So when we study a gas, we talked about the 3 states of matter at the beginning of the year. We talked about heat with the specific heat equation, and we talked about endo and exothermic changes. And one of the things we described with heat is that decides what state of matter something is. So if you recall, if you could envision the atoms that make up a gas, what you would see in that is that they are spaced very far apart, and that's where we get a lot of unique properties of gases, in that they are able to conform to the shape of their container and their volume can change, and so that's a unique property that we don't see within solids and liquids. And so before we can get started, you have to note that there's 4 variables that determine how a gas may behave. And so the first one is pressure, and we recognize that as the uppercase letter P in a formula. And so pressure, you guys, if you own a vehicle, hopefully you are taking the pressure of your tires. And so you use a pressure gauge, and most likely you're probably recording it in PSI, which is pounds per square inch. So when you measure tire pressure, what you are actually measuring is the force that gas is creating by colliding with the walls of the tire. And so most likely you can see differences in your pressure readings as we go into summer versus winter months. Units, so there's a lot of different pressures of unit pressures out there, and so I've listed some of those out. So this will be a handy table as we get started to refer to if you're not sure what characteristic is being described in a problem. So 1 unit of pressure measurement is the atmosphere, and we abbreviate that ATM. With SI, we use millimeters of mercury, or mmHg. We use torr, which is the equivalent of millimeters of mercury. It stands for a scientist named Torsolini. And then the last one is the kilopascal, which is abbreviated kPa. If you do some hunting around, there's many other units out there, including, for example, the pascal. I try to limit it to just a couple that we use most often. The next variable that determines property of a gas is its volume, so just how much space it takes up. Common units of measurement for it is the liter, abbreviated L, and milliliter, ml. Those are the main 2 properties we're going to work on today, but you will eventually see temperature and amount. Amount, you probably automatically think of the gram, but another way we can record amount, which is something we have worked on, is the mole. And then temperature is going to be either in degrees Celsius or in what's called Kelvin. We'll take that on more a little bit later. So we're going to work on what's called Boyle's law today, and before we can do that, we need to work on how to do pressure conversions. So it says here that a sample of neon gas has a pressure of 0.5 atm. It says calculate the pressure in millimeters of mercury of the neon. So up here are all the conversion factors. So this sets all the pressure units equivalent to one another. So we know that we're starting out with atmospheres, which is abbreviated ATM. And it wants to know in millimeters of mercury. So we can see right here, our very first conversion factor is given right away. That 1 atmosphere of pressure is equivalent to 760 millimeters of mercury. So because our given unit is ATM, we know that ATM needs to go in the bottom. So 1 ATM in the top is 760. We can cancel out the atmosphere unit, and we can go ahead and work it through by multiplication, and that is equivalent to 380 millimeters of mercury. So again, using a scale that we just worked on in our last unit of just how do you successfully set up a conversion. In the next example, it says on the climb up Mount Whitney, the atmospheric pressure drops 467 millimeters of mercury. What is the pressure in kPa, or kilopascals? So we see and can identify our given as 467. And I'm going to go ahead and put an asterisk over the two that I'm using in purple. So we're working with millimeters of mercury and kPa. So what this does is, by setting all four of these equal to each other, we don't necessarily have to set up multiple conversion factors. The nice way of doing this is we can solve it in one conversion factor using these two pieces of information. So because my given is millimeters of mercury, that means the 760 millimeters of mercury needs to go in the bottom. And then the kilopascals, the 101.325, therefore goes in the numerator. So go ahead and take a second to pause and get your calculator out and run this through. So if you want to take a second and pause the video, go ahead and then see if your answer compares to mine. What you should do to multiply or solve it is start by multiplication. So you should take the 467 times 101.325. I would then go ahead and hit enter on my calculator. Then you want to divide that out by the 760 millimeters of mercury. So the units cancel out, and you get an answer of 62.26 kilopascals. So again, we were able to get this done in one step. The one thing that's kind of unique is one of our conversion factors traditionally have been 1 is equal to something. In this case, we have two values that are equivalent to each other. So the main thing we're going to work on today then is the relationship of the two properties that I spent, I guess, the most time describing, and that's pressure and volume. And so the one thing I have here is that they're an inverse relationship. So let's say everything else is under control. So let's say you have a balloon, for example, that stays in the same room, so no temperature change, we can assume, and let's say you tie it off. So when you exhale into that balloon and tie it off, it has a set volume. And then you could identify what the pressure is in that system. If you think about it, if you compress that balloon, if you're compressing, what's happening to the pressure inside of that balloon? Well, the pressure is increasing. As that pressure increases because you are compressing on it, what happens to the volume? Well, that volume had to get smaller. So for that pressure to increase, that is because there are more collisions happening, and therefore, again, you see a pressure rise. If you think about our classroom and envision yourselves as representing gas particles, if you were to take my classroom and shrink it in half, and I tell you to get up to get a material, most likely you might bump into one of your classmates. And again, this is modeling Boyle's law, in that if volume decreases, pressure is going to increase. And again, pressure is those collisions. If we were able to take the walls out and connect the lab to the classroom, our volume would be more significant, and you guys could spread out, and most likely you would collide with each other less often. So the same thing happens. So if volume increases, pressure is going to decrease. That's what an inverse relationship is. So as volume goes up, pressure goes down. So the more space you have, fewer collisions. If your space gets smaller by volume decreasing, therefore your pressure is going to go up. You're going to have more collisions. And so we can represent that mathematically with this equation here, that V1P1 equals V2P2. V representing volume, P representing pressure. The 1 and the 2, those subscripts there, are representing initial and final. So the 1s represent how the system started out to begin with. The 2s represent how the system ended. And so if you take a look at this first example, it says that hydrogen gas has a volume of 5 liters and a pressure of 1 atmosphere. what was the final pressure in atmospheres. So we want the same unit of pressure when the final, or if the volume is decreased to 2 liters. So what I like to do is start out by identifying my variables, and I've done this throughout the year. So it tells me that it has a volume of 5 liters. And it mentions in the question part of it, it says, what is the final pressure? So that means the 5 liters and the 1 atmosphere, those are the initial conditions, the starting conditions. So I'm going to identify that 5 liters is my V1 versus the 1 atmosphere is the pressure condition in which it started, which is 1 atmosphere. So it's telling me that I'm solving for final pressure. So V2 is what I am calculating. So that means that 2 liters, if you think about the unit of liters, that's measuring volume. So that's my new volume after the change has occurred. So I know I'm using Boyle's law. We have P1 V1 equals P2 V2. So we can start substituting that information into the formula. So I can take 1 atmosphere, multiply that by 5 liters, equal that to pressure, being I'm going to change that to an X, so it looks more like a algebraic expression, times my 2 liters. So the thing that you have to be careful with is how you rearrange this equation to solve for X. So you look at mathematically, what are we doing? We're doing multiplication. What do you do to get something alone? If you're multiplying, you do the opposite. So we are going to divide by 2 liters. By doing that, I can cancel the 2 liters on the right-hand side. And so what I need to do to solve is I need to take 1 atmosphere times 5 liters divided by 2. Looking at units, I can see liters up above and below, so that means those are going to cancel as well. So my X is going to be 2.5. And this is ATM, or atmospheres. Again, if you think about it, the volume decreased, so we saw pressure go up, and that should make sense. In example 2, or letter B, we have a balloon is filled with 2,000 milliliters. So liters can be in any unit that you want, as long as they are equal to each other. So in the first problem, we use liters. In the second example, we're using milliliters. So I know that this is going to be my initial condition, my V1. And what goes with it is the 2 atmospheres. And atmospheres measures pressure, so that's P1. It says, what is the volume of the balloon if the pressure is changed to 5 atmospheres? So what we are altering in this condition is the pressure. And we want to know, because of that pressure change, what will the new volume be? So let me actually rework this. So my P2 is the 5 ATM. So if you look, our pressure is going up. So if you want to make a prediction, what should happen to our volume? Well, our volume should get smaller because pressure increased. So I'm still working with Boyle's law. I can go ahead and substitute in my information. Again, much like the previous example, we are going to need to divide in order to get this to have X on its own. So I can cancel those on the right. So what you need to do to solve is take 2,000 times 2 ATM, divide that by 5 ATM. Our X will then be equal to 800 milliliters. And like we predicted before we even solved, is that our pressure went up. In order for pressure to go up, volume must go down. Okay, so you have a small problem set to work out using Boyle's law. Please reach out to me with any questions or concerns.